Hi, I'm Rufin VanRullen, here to tell you about our new model called GAttANet. Like many people, we're trying to integrate attention or transformers in computer vision architectures, but we're trying to do it in a way that would be more biologically plausible. But first, what is attention, at least in machine learning? Before 2017, attention was already used in ML, but mainly in recurrent networks as a way to avoid vanishing gradients. But in 2017, something happened with this paper that introduced the transformer architecture. The key idea was to get rid of recurrence. It's a feed-forward architecture where you provide all your inputs at once, and following several steps of transformation, you spit out all your outputs at once in a strictly feed-forward way. The key operation for self-attention is defined here. Most people already know this, so I'll be brief. The input sequence X is transformed into queries, keys, and values. The queries and keys are compared with a dot product so that the values get incorporated into the output Z in proportion of this matching score between key and query. And this, of course, is skipping over many important details, but we won't be needing these for our models. So transformers have now entirely taken over NLP. And of course, it wasn't long until people started to apply similar ideas to computer vision, either to augment convolutional network with self-attention layers or to replace the conv layers altogether with transformer blocks. Here are some examples as of a couple of months ago, at least, but in fact, it's almost impossible to keep up with this field. There were more than 200 vision transformer papers that came out already in 2021. And this is exciting, but it could also be problematic because one way to see this is that each of these new versions of the transformer is incrementing the state of the art on ImageNet, which is still our standard benchmark. And each increment is taking us towards an optimum, but of course an optimum for this architecture. Maybe it's only a local optimum. And one problem here is that all these models are basically hundreds of incremental gradient steps that have been taken towards optimizing ImageNet accuracy of vision transformers. So now, even if you had an objectively better architecture, it would be very difficult to beat this accuracy. And the more transformer papers come out, the less likely this is to happen. So we seem to be stuck in an endless cycle or a self-fulfilling prophecy. And to get out of this, we should probably start considering other factors to optimize rather than just ImageNet accuracy. And one factor that I want to focus on today is biological plausibility. So how is attention implemented in the brain? This is a macaque brain, but don't worry, it's pretty much the same for humans. We know a lot about vision and attention in the brain. We know that vision is implemented in a hierarchy of successive visual areas. And this hierarchy is actually very similar to the architecture of ConvNets. Many people have looked at this and found a fairly good correspondence between the different visual regions and the different layers of a ConvNet. Now, what about attention? In the brain, attention is implemented in separate regions. It forms a network called the frontoparietal network because it includes regions in parietal and in frontal cortex. And all these do different things, of course, top-down, bottom-up attention, and we don't fully understand how it works. But what is clear is that attention is anatomically separate from the visual stream. Of course, the attention regions interact with the visual stream. They get their inputs from the visual stream, and they send modulatory signals to the visual stream. So if you think now of the vision transformer, what people have done is include lots of small stages of attention transformation, either in between the convolution or instead of the convolutions. And I would argue that this is not how it's done in the brain. If you want to do it like the brain, you have to start from these ConvNets and then create a separate attention system, which is going to interact with the visual regions. And that's exactly what we're going to do. This is the architecture that I'm going to present. So we're going to have a ConvNet, and we're going to have a global attention system, and they're separate but interacting. We call this GAttANet because it uses global attention agreement to decide how to modulate visual processing. So this is actually one of the ConvNets that we implemented. It's our toy model. And we also played with a ResNet that I'll show in the next slides. So this model has 3 conv layers, 2 dense layers. The last one is a classification layer for CFAR10 or CFAR100. We did it for both data sets. We're going to train this model for image classification. and then we're not going to touch it anymore. It's like our independent visual stream. And then after that, separately, we're going to train our global attention system, which looks at what is being computed here and tries to see if by applying gain control to different parts of the system, it could improve performance. So we want to receive information from all these layers. And the way to do this, of course, is using keys and queries, as in the transformers. So each layer has its own key matrix and query matrix, and they work in a slightly different way for the conv layers and the dense layers. The conv layers use a dot product, the dense layer use a scalar product, but basically we end up with key and query maps of dimension D. D is the dimensionality of our attention mechanism, and in different networks, we're going to play with it. We'll go from 4 to 64 dimensions. So now we can use the keys and queries to compute attention, but we're not going to do it separately for each layer, otherwise it wouldn't be global attention. So in this work, to make it simple, we'll just take all the queries from all layers and positions and average them into a single vector of dimension D. So every neuron in the network gets to vote for what should be the unique query that we're going to ask for this particular image. And now that we have a unique query vector, we're going to match this vector with every key using a dot product, and we'll end up with a map of agreement scores for each layer. So these are scalar values, and that's what we'll use for gain modulation inside our ConvNet. So I should have arrows going back to the left here, but that's too messy. So I'll just replicate this network on the right. I insist it's the same network with the same weights. Now we're doing a second pass through this network, but now it's modulated with multiplicative scaling by the agreement scores in these maps, so that some parts of the network, those that are more in agreement, will be upregulated. That would be the red unit in this example. And some parts will be downregulated. That would be the blue unit, in such a way that maybe the network can improve its decision now compared to the first pass. And that's exactly how the attention system is trained end-to-end with backprop to optimize the classification accuracy after the second pass. So as I said, we didn't just play with this toy model, but also with standard pre-trained ResNets. This is the ResNet backbone. What we want to do is to project these layers into the global space, but we can't project all of them. There's just too many. So we just chose 4 conv layers and 2 dense layers to send to the global attention space. And then the attention modulation goes back to the same layers on the next pass. Now it's time to look at the results. This table is a summary. We had different models, the toy model, ResNet 18 or 50. We applied them to different data sets, CFAR10, CFAR100, ImageNet. We used pre-trained models. So here is the corresponding number of parameters and the corresponding accuracy before we include any attention. So this is our baseline, if you want. Then we don't touch this backbone. We just incorporate our attention mechanism and see if we can improve. So for attention, we have a choice on the dimensionality of attention vectors. So we played around with this a little bit. With some networks, we went down to 4 dimensions or up to 64 dimensions. And this affects the number of attention parameters. These here are the only trained parameters in our models. They are additional parameters on top of the backbone. And you see that it's typically a lot less, about 50 times fewer. And this is the final accuracy after going through one pass through attention and then again through the backbone. You see that the level of improvement clearly depends on the model and on the data set. For the toy model, we get 2% improvement on CFAR10, 3% on CFAR100, actually up to 3.5% with the highest attention dimension, D equals 64. For the ResNets on ImageNet, the improvements are systematic, but much more modest, about 0.3 to 0.4% improvement. So you might wonder, given that we have a few more parameters, isn't it normal or trivial that we're going to see improved performance? But it's not trivial, as you see here, where I'm plotting the accuracy as a function of parameters for our model in orange and for ResNet 50 and ResNet 101 in blue. If you simply increase the ResNet architecture to get the same number of parameters, you wouldn't see any performance improvements. You would need 50 times more additional parameters for a ResNet to show the same improvement. Now we'll explore some more properties of the architecture. We're back to the toy model on CFAR 100. You'll remember that for the normal dataset, we got 3% improvement up here with the baseline in blue, and the other 3 lines now are different versions of the network with different dimensions of attention. So now we added various amounts of Gaussian noise to test the generalization properties, since neither the baseline nor our models have ever seen Gaussian noise before. So of course, when the images get so degraded that you can't see anything anymore for a sigma of 0.25, then the performance will be a chance for all models. But the nice thing is that the improvements of attention remain all the way until this point. So it's fairly robust to Gaussian noise. So the 3 attention dimensions don't look much different here. But if you actually subtract the blue line, so you look at relative improvements, you see that the curves are not exactly identical. It does help to have more attention dimensions, and especially so at moderate noise levels. So at 5% noise, when you can still recognize the picture, but it gets a little corrupted, then that's when attention is most useful, and you can get up to 8.5% improvements with the highest attention dimension. So now we can probe the different parts of the model, starting with the global average query at the top. This is a small vector, for example, a 16-dimensional vector for each image. So we can explore with dimensionality reduction what these query vectors are encoding. That's what you see here. In this 2D projection, the images are color-coded by class. This is for CFAR 10. And in case you don't speak CFAR 10, I've put the class labels next to it. So what you can see is there's some structure in the space with the yellow-green points at the bottom right and the dark blue-red on the top left. And you actually realize that these are animals and vehicles, which are nicely mapping to different parts of the space. So this means that the attention system understands something about the structure of the space. And that's something we could use for other purposes. We could hack the system and replace the average query for every image with just the right vector so that the model, for example, would pay attention to frogs. So that's a form of top-down attentional modulation, and that's for future work. The last thing we can do, because we're looking at an attention system, is to visualize these attention maps. So here are 5 different images from CFAR 10. The maps are showing the color-coded agreement score for each conv layer. And for the dense layers, we see the same thing as bar plots. And in the top layer, the classification layer, we can even color code the target class in red. So depending on the image, in the conv layers, we see that various features are up or down-regulated. It's not obvious what they mean, but the map clearly reflects something about the picture. It's probably more interesting to see what happens at the top. Here, the target logit, the one from the actual image class, is typically among the highest agreement scores. The other guys tend to have negative scores. So this means that on the next pass, the red guy's activity will be increased and most of the other guys will be decreased. So the network could now be more accurate and more confident. So to conclude, we presented a first attention architecture inspired by transformers with keys and queries that we hope is more in line with what we know about attention in the brain. It did improve image classification compared to baselines with few additional parameters, so it works somehow. But of course, it's not or not yet competitive with vision transformers. Now, as I said at the beginning, the comparison is not exactly fair because vision transformers now have a huge head start. They've gone through hundreds of incremental improvements. So maybe the most we can say is that our model could be a good place to start optimizing this architecture. And maybe after a couple hundred papers, we'll definitely get to beat the vision transformers. But more seriously, we do have ideas for how this architecture could be improved. We could use more time steps or iterations through the global attention. We could use full attention, all keys to all queries, instead of sharing a single global average query. We could have position-dependent queries and keys, or we could encode more than one aspect of the image at a time with multi-head attention. And all these will be explored in future papers. So stay tuned, and thank you for your attention.